This can be a little video on buffers, since a number of you are going to be gone. Here's what a buffer is. A buffer is something that resists changes to pH. Okay, so the way a buffer does that is it has a substance that can use up H plus ions and a substance that can use up or react with OH negative ions. So a buffer typically has a weak acid and its conjugate base. Now, a good example of buffer is in your blood. Okay, so your blood has carbonic acid in it, and that is formed from carbon dioxide that builds up from your cells reacting with water. It makes carbonic acid. Well, this can also form a weak base. So you have these weak bases and weak acids floating around your blood to keep your pH around a 7.4. We'll talk about that system at some point in time here. So let's say this. A buffer a lot of times is made of a weak acid. Okay, so that is a weak acid and its conjugate base. Now I can't just get the conjugate bases. I can't just go take some Cn negative and pour in there again. So what I would use is potassium cyanide or sodium cyanide, something like that, that contains the weak base that is soluble. So if we dissolve this in water, you end up with your Cn negative ions. So now you've got a mixture of the weak acid and the weak base. Now most buffers you want to have equal amounts of the weak acid and the weak base. So just briefly here, if I have a mixture of these two things, if I add some H plus ions, if I add something acidic enters the solution, some kind of acid enters the solution, then this can react with the H plus ions to form HCN. If something basic comes into the solution, something with OH negative, this can react with OH negative ions to form HOH plus Cn negative. Okay, so you have these two things in there that can resist changes to pH. Now there's a limit to the buffer. Once one of these runs out, if we run out of this weak acid and we add more OH negative ions, there's nothing for those to react with and the pH is going to rise very, very quickly. Okay. Now adding OH negative or adding H plus will change the pH. Okay. It just changes it by smaller amounts. Let's go back to what we've done in the past. So if we show the equilibrium of this, we end up with H plus Cn negative, and there's that conjugate weak base to HCN. If we write our K expression, so Ka equals concentration H plus, concentration Cn negative, all over that concentration. I'm going to rearrange this a little bit and solve for H plus. So if I would cross multiply this, I'd have Ka times that equals H plus and divide by Cn negative, you end up with this. The concentration of H plus equals your Ka times your concentration of acid over your concentration of weak base. Okay, so anytime I want to know the concentration of H plus ions, which we can get pH from very, very easily, if I have a weak acid base solution, if I take the concentration of the acid divided by the base times the Ka of that acid, then I can get H plus ions. I could also do this with OH negative. I could say OH negative equals Kb times base over acid. Again, it's important to remember that this is the exact same thing we've been doing. When we've been doing this, this always has concentration of the weak base and concentration of the weak acid in it. Okay, it's always got those two things in it. I like to do this for any acid-base mixture. So anytime we start putting a base into an acid or acid into a base, I can figure out the pH of that mixture based on this. Okay? Now obviously, the more acid I have compared to base, the more the H plus. So that means the lower the pH. So if this is more than this, which makes sense, I have more acid than base, it's going to have more H plus ions, more pH. one thing you will see on your blue sheet, this equation is on your blue sheet, but there is something called the Henderson-Hasselbalch equation that is on there. And what they've done for that is they have said pH, which is negative log of that, equals pKa, which is negative log of Ka, times the base over the acid. They flip those around. So this is essentially the same thing. I would rather do this than just take the negative log of the answer. It's easier to work with, I think, when we're doing that. Let's say we have equal amounts. So a lot of times when we make a good buffer, we have equal amounts of these. And usually we use between 0.1 molar and 1 molar. Okay, so let's say we have 1 molar of that and 1 molar of that. Or 0.5 molar of that, 0.5 molar of that. So if we have equal amounts of those, that ratio is going to be 1. So in that case, the concentration of H plus would equal our Ka. Think about that. Whenever this ratio is equal, our concentration H plus equals Ka. So if we have an acid with a big Ka, that means we're going to have a lower pH. So a buffer does not have, if we have equal amounts of acid base, the pH is not 7. If it was strong acid, strong base, it would be. Okay, but one of these is stronger than the other one. Conjugate acid and conjugate base, Ka times Kb equals 1 times 10 to the negative 14th. One of these two things is stronger than the other one. Okay, so the bigger this Ka, the more H plus ions, if we have equal amounts of those. So you can make a buffer with varying pHs. Sometimes you want a buffer with a pH of 5. Sometimes you want a buffer with a pH of 8. Sometimes you want a buffer with a pH of 7. Okay, so you can change that. You can also change this ratio to change that concentration H plus, or you can use a different acid and conjugate base combination. So that's kind of a brief introduction to buffers. Now we're going to work through some problems. I'm going to make another video, but we'll work through some problems where I give you those concentrations and say, okay, now if we add some H plus ions, some hydrochloric acid or something like that to it, what happens to that buffer? How much did it change in pH?